In this video, we're going to continue talking about random variables and probability distributions. Specifically, we're going to be talking about normal distributions. Now, normal distributions are continuous probability distributions. They're symmetrical, bell-shaped, unimodal, density curve defined by mu and sigma. The area under the curve equals 1. The probability of observing a value in a particular interval is calculated by finding the area under the curve. Well, how do we do this mathematically? Well, to overcome the need for calculus, we can rely on technology or on a table of areas for the standard normal distribution. As sigma increases, the curve flattens and it spreads out, looking something like this. As sigma decreases, the curve is going to get taller and thinner, like this. So, do these two normal curves have the same mean? This is on a scale from 0 to 10. If they do, what is the mean? We see that they do have the same mean, which happens to be at a 6. We can see that as we come up right here, right? That's the apex of both A and B. So we want to know what exactly is the mean, and it's 6. We're able to count from 0 over to 6. So which of these two curves has a standard deviation of 3? And we can see that that's going to be curve B. So we go 3 out and 3 out, so it's been stretched or pulled. And so which normal curve has a standard deviation of 1? And that's going to be our curve A, because we're getting our 3 deviations in tight pieces, and notice how it's taller and skinnier. Notice that the normal curve is curving downwards from the center or the mean to the points that are 1 standard deviation on either side of the mean. And at those points, the normal distribution, or excuse me, the normal curve begins to turn upward. For standard normal distributions, it's a normal distribution with a mu of 0 and a sigma of 1. Now, this is customary to use the letter Z to represent a variable whose distribution is described by the standard normal curve, or the Z curve, as we see here. Now, when it comes to using the table of standard normal Z curve areas, for any number Z star from negative 3.89 to 3.89 and round to 2 decimal places, the appendix table 2 from our book gives the area under the curve and to the left of Z star. So we're able to say that the probability of Z being less than Z star will equal the probability of Z being less than or equal to Z star, where the letter Z is used to represent a random variable whose distribution is the standard normal distribution. Now, to use a table, you're going to find the correct row and column, and we're going to do that in the next example. And the number at the intersection of that row and column is the probability. So let's go to that example and see how this works. Suppose we were interested in the probability that Z star is less than negative 1.62, which is designated by our shaded region. So the probability that Z is less than negative 1.62. Now, in the table of areas, you want to find the row that's labeled negative 1.6 and the column that's labeled 0.02. Then we're going to find the intersection of that row and column, and it will tell us our solution. So again, here we have our table. So we want to find the row that is negative 1.6 and the column of 0.02. Doing that gives us an answer of 0.0526. This represents that probability and that area under the curve. So now that we know how to do it, let's have you do one on your own. Suppose we're interested in the probability that Z star is less than 2.31. So I want you to find that probability for me. Here's the table. So go ahead and push pause and do that. When you're done, push play and let's see if you were right. So we're going to find the row that is 2.3 and the column that is 0.01, and we're going to find an intersection of 0.9896, which will represent our probability that Z is less than 2.31. Let's do another one. Notice that here we're interested in the probability that Z star is greater than 2.31. Now, if we take a look at this, we're going to see by using our table, we're going to get a 0.9896. But look at the area that's shaded. It's not to the left of 2.31, it's to the right. The table of areas gives the area to the left of the z star. So to find the area to the right, you're going to need to subtract that value in the table from 1. So we'll actually have 1 minus 0.9896, which will give us 0.0104 as our probability. Let's do another example. Suppose we're interested in finding the z star for the smallest 2%. So here, you're being given the probability, and we're trying to find what will give us that number. So in this case, in order to find z star, you're going to look for the area 0.0200 in the body of the table. And then you're going to follow the row and the column back out to get the z value. So as we look, 0.0200 doesn't appear in the body of the table. So we're going to use the value closest to it, which is 0.0202. So I move over and up, and that's going to tell me my answer is negative 2.05 for my z star value. So what if we suppose that we're looking for something on the right side of the tail? So suppose we're interested in finding the z star for the largest 5%. So here, our z star is what we're looking for, and we know that that probability is 0.05. Now remember that the table of area gives the area to the left of z star. So we actually want to take 1 minus the area to the right of z star, and then look up this value in the body of the table. So 1 minus 0.05 gives us 0.95, and that's the value we're looking for. So 0.95. Notice that that's also not on the table. However, we can see that 0.9500 is exactly between 0.9495 and 0.9505, which means that we can average the z star for each of these. So we're going to go ahead and add those and divide by 2, and that's going to give us a z star of 1.645. Now, a z-score, aka the standard score, it indicates how many standard deviations an element is from the mean. And a z-score can be calculated using the following formula. Z equals x minus mu divided by sigma, where z is the z-score, x is the value of the element, mu is the population mean, and sigma is the standard deviation. So let's talk about how to interpret a z-score when you get it. So a z-score less than 0 represents an element less than the mean. A z-score greater than 0 is going to represent an element greater than the mean. A z-score equal to 0 will represent an element equal to the mean. A z-score equal to 1 will represent an element that is 1 standard deviation greater than the mean. And likewise, a z-score of 2 will be 2 standard deviations from the mean, greater than the mean, and so on and so forth. A z-score equal to negative 1 will represent an element that is 1 standard deviation less than the mean. And a score equal to negative 2 will represent 2 standard deviations less than the mean, and so on and so forth. Now, if the number of elements in the set is large, then we can say about 68% of the elements have a z-score between negative 1 and 1, and about 95% have a z-score between negative 2 and 2, and about 99% have a z-score between negative 3 and 3. Let's talk about finding the probabilities of other normal curves. So to find the probability of other normal curves, standardize the relevant values and then use the table of z areas. Now, if x is a random variable whose behavior is described by a normal distribution with a mean of mu and a standard deviation of sigma, then you can say that the probability of x being less than b is going to be equal to the probability of z being less than b star, and that the probability of x being greater than a will also equal the probability that z is greater than a star, and that the probability of x being between a and b is going to be equal to the probability of z being between a star and b star, where z is a variable whose distribution is standard normal and the A star of A minus mu divided by sigma and B star of B minus mu divided by sigma represent the z-scores for A and B. Let's do an example. So the data on a length of time to complete a registration for classes using an online registration system suggests that the distribution of the variable being x equal the time to register for students at a particular university can well be approximated by a normal distribution with mean of mu of 12 minutes and a standard deviation sigma of 2 minutes. So we want to know what is the probability that it will take a randomly selected student less than 9 minutes to complete the registration. So we're looking for the probability that x is less than 9. Well, we can standardize this value. So we're going to take 9 minus 12 and divide it by 2. That's going to give us a negative 1.5. When we look that up in the table, we're going to get a value of 0.0668. Well, what is the probability that it will take a randomly selected student more than 13 minutes to complete the registration? Again, we're going to standardize this value. So 13 minus 12 divided by 2 is negative 0.5. Now we're going to look this up in the table and subtract it from 1. Doing so is going to give us a value of 0.3085. So what is the probability that it will take a randomly selected student between 7 and 15 minutes to complete the registration? So here, we're going to actually standardize both of these values. So we're going to find our A star of 15 minus 12 divided by 2, which is 1.5, and our B star, 7 minus 12 divided by 2, which is negative 2.5. And we're going to look both of these values up in the table and then subtract them. Doing so is going to give us an answer of 0.9270. Now, because some students do not log off properly, the university would like to log off students automatically after some time has elapsed. It's decided to select this time so that only 1% of students will be automatically logged off while still trying to register. What time should the automatic log off be set? So it's giving us the answer, right? It's telling us the 0.01. So it wants us to find our A star. So we need to look up the area to the left of A star in the table. So remember, we need to take 1 minus our 0.01, which is 0.99. So that's the number we're going to look up in our table. And then we're going to use the formula for standardizing to find our x value. So when we look up 0.99 in our table, we get 2.33. Now our standardization is x minus 12 divided by 2. So we'll multiply both sides by 2 and then add 12 to give us an A star value of 16.66. Meaning that at about 16.66 minutes is when the log off should be set.